Hello, welcome back to Mech 975 Advanced Vibrations. In this video we're going to begin our discussion of multi-degree of freedom systems, starting by assembling matrix equations, and then we'll go into a discussion of how to perform modal analysis. So let's consider the following n degree of freedom system. We're going to assume that it's linear, and that all of the motion is in a small neighborhood around the equilibrium position. Okay, so we're going to have linear springs, linear dampers applied to every mass, close M1, C1, K1. This then connects to several masses until we finally get to the mass Mi minus 1, which has damping, springs that connects to mass Mi, just trying to be a little bit more compact here. Let's zoom in. And this connects to mass Mi plus 1. And then at the very end, we will have mass M sub n for the nth degree of freedom. With string Kn plus 1 and damping, or a damper with coefficient C n plus 1, and we'll connect them to the ground. Oops. Cn plus 1. Okay. And then this is Ci minus, here is Ci minus 1, or actually this is just Ci. I need to zoom in here to erase. This is Ki, Ki plus 1, and this is Ci plus 1. Now let's go ahead and draw in our coordinates. This is x1. Actually, before I do that, let me move this drawing down a line. In fact, we'll do the displacements down here, x1. Actually, we'll call these q1 of t for generalized coordinates. This is going to be qi minus 1 of t. This one will be qi of t. And then this will be qi plus 1 of t. And then lastly we have q sub n of t. Okay. I'm going to change the color of these parameters and so that they're easier to see into blue, but I'm going to pause the video while I do that so you'll see them suddenly change color. Okay, I also moved the position of qi of t and cleaned up qi minus 1 of t so we could fit that in. Let's go ahead and add in here some external forces. On the first degree of freedom we'll have q1 of t, then we have on the second one qi minus 1 of t, then we have qi of t, and these are just generalized forces, but we're assuming that they're either linear, they're external applied forces. They're no friction or no nonlinear forces, or just we're assuming that they're just external applied forces. And lastly, we'll have Qn of t. Okay, great. Alright, let me scroll up so I have some more space to rest my hand. So we can say that from any method, the equations of motion are, we'll get mi qi double dot plus ki times qi minus 1. In the case of I is equal to 1, q sub 0 is just 0. That represents the displacement of ground, which is 0. Then we get plus ki plus 1 times qi minus qi plus 1 plus ci times qi dot minus qi minus 1 dot plus ci plus 1 times qi dot minus qi plus 1 dot, and then this is equal to qi, and this is valid for I is equal to 1 all the way up to n. And specifically we need to note that q sub 0 of t is equal to q sub n plus 1 of t, and these are equal to 0, and they're 0 for all time. In fact, to stress this point, let's write it like this. They're defined to be 0 for all time. Okay, so in a compact form, the equations of motions become the sum. Let me start over here, and actually let me go down a line. The sum from j is equal to 1 all the way up to n of mij times qj double dot, and I'm going to drop function notation here, plus cij of q dot j plus kij times qj is equal to qi. Why don't we add the of t up here as well, just so that we can distinguish that this is an external force and not some kind of degree of freedom. And then this is true for I is equal to 1 all the way up to n. Okay, and where mij is equal to delta ij times mi, and this is not the Dirac delta. This is, I believe it's the Kronecker delta, though I don't remember specifically, but I'm pretty sure it's the Kronecker delta. And if that's not the right name, then please let me know, and I'll add a comment to the video to correct that. And this is true for j is equal to 1 all the way up to n. Then kij, this is equal to 0 for j is equal to 1 all the way up to n. provided that j is not equal to I minus 1, or I plus 1. Then k, I, and I minus 1 for j. This is equal to minus k sub I, comma, kii is going to be equal to ki plus ki plus 1. And then ki, where j is I plus 1, this is equal to minus ki plus 1. The same is true for Cij. This is for I is equal to, we'll put that at the end actually because it's true for all of this. So then Cij is equal to 0 when for j equal to 1 all the way up to n, and when j is not equal to I minus 1, I plus 1, or I plus 1. And then Ci of an I minus 1 for j, this is going to be equal to minus Ci. Cii is equal to Ci plus 1, and then Ci plus 1, this is equal to, let me clean that up a bit, this is equal to minus Ci plus 1. And then this is all true for I is equal to 1 all the way up to n. Alright, or in an even more compact form, we can write that we have a matrix M. In fact, M double underline will represent matrix right now, times Q double dot, which is a vector, plus matrix C times Q dot vector, plus matrix K times Q vector is equal to capital Q vector. Okay, so M here is an n by n matrix, and it's the mass matrix. C is the n by n damping matrix. K is the n by n stiffness matrix. And then, of course, the Q's and Q dot and Q double dot, those are n by 1 vectors. In fact, let me move this down so I can write above it. Well, actually, no, I won't. This is our n by 1 acceleration vector. This here is our n by 1 velocity vector. So the n by 1 displacement vector. And specifically Q well, it's a vector. There. That's our Q. Whoops. So that crashed for me, and I had to go back to my notes. But we'll just continue from right here. Displacement vector. That's our Q. It's n by 1. Okay, and you'll notice that this is similar to a damped harmonic oscillator, except that now it's in a matrix form with multiple degrees of freedom. I want to make a couple of notes. One note in specific here. Note that M transpose is equal to M. That means it's symmetric. Same with the stiffness matrix. As well as the damping matrix. In this case, they are all symmetric. And more importantly, we should state that the fact that these are symmetric is a fundamental result of mechanics. It's a fundamental result of mechanics. And in fact, it comes from the Betty-Maxwell theorem of reciprocity, which we may discuss. I'll probably send out a handout on that instead, actually, rather than go through it. Yeah, I'll send a handout on the Betty-Maxwell theorem. Okay, we're gonna stop here. In the next video, we're gonna go through how to apply modal analysis to a multi-degree of freedom system.